Alright dear children, now we go to next important topic. As I said in the last video also, that means the total energy of a particle in simple harmonic motion. SHM means simple harmonic motion. Okay. Now when a particle executing simple harmonic motion, it possesses both energy. It possesses what? Both energy. Both energy means one energy, it will be what energy? Kinetic energy. So motion, due to motion, particle possesses what energy? Kinetic energy. And another energy which also possessed by the particle due to its position, that is called what energy? Potential energy. What energy? Potential energy. But the potential energy which possessed by the particle is actually elastic potential energy. This is actually a what? Elastic potential energy. Because potential energy are also two types. One is called what? Gravitational potential energy, another is called elastic potential energy. Okay, that means the particle executed, when a particle is under simple harmonic motion executed, two type of energy, one is called kinetic and potential energy, and this energy are also called mechanical energy. Okay, now this possesses potential energy, particle possesses potential energy, as I said, on the account of the displacement of the particle from the mean position, and as I said, kinetic energy is acquired by the particle on the account of the motion which is acquired by the velocity of the particle. Now this energy varies during the oscillatory motion. The energy varies during the what motion? Oscillatory motion. But the total energy, they sum, and this sum is also called total energy. Total what? Energy. Always remain constant, or also called conserved. That means we can see the conservation of energy even in case of simple harmonic motion. So in simple harmonic motion also the energy get conserved. But that energy remain conserved means the total energy remain constant or remain conserved. Okay, remain constant, also called what? Conserved. In spite of the force which exert on the particle, that is called what force? Or restoring force. Now in order to measure the total energy of the particle in the simple harmonic motion at any instant of time, okay, we first measure the what energy? Kinetic energy, and we measure what energy? Potential energy, and we add that to energy. That makes the total energy. Okay, but in order to measure this kinetic energy and potential energy, let me write the displacement equation of the particle in simple harmonic motion, because every particle has what? Mass, and I write down that mass of the particle is what? M. Let M be the what? Mass, the mass of a particle. Let M be the mass of a particle. Okay, executing what motion? Executing simple harmonic motion. Now if there is a mass of the particle, then particle have a displacement, and I write this displacement particle in terms of initial phase. What phase? Initial phase, also called epoch. So let me write down, therefore, the displacement, okay, the displacement of a particle in terms of what? In terms of epoch in what motion? Simple harmonic motion. And this is given by y. You have done this way. Y equals to what? Equals to a sine omega t plus what? Phi. But children, remember this displacement is not only expressed by y-axis. It can be along what? Y-axis. It can be along x-axis. If the displacement is a linear displacement. If a particle has a linear simple harmonic motion, the displacement is again expressed by what? X. So we can write x even as a sine omega t plus phi, and this phi is called epoch, and displacement y can also written as a sine omega t plus what? Phi. So once this is the displacement, okay, of a particle in simple harmonic motion, we can even write the velocity of the particle. So I am writing directly the relation. The velocity is actually measured by a omega cos omega t plus phi. Yes, children, we derive the expression velocity in simple harmonic motion, but without the initial phase like epoch. But I follow the same relation in terms of epoch also. So without initial phase, it was a omega cos omega t, you know it. But in terms of epoch also, it will be b equals to a omega cos omega t plus phi. So these are the displacement and these are the velocity of the particle under simple harmonic motion. So with this displacement velocity, we can even measure the what? Kinetic energy. We measure the what energy? Kinetic energy. The kinetic energy of a particle, and kinetic energy particle is actually given by K, and kinetic energy expression, as you know, it is how much? 1/2 mv square. If a particle has mass and moving with the velocity, then kinetic energy is given by this formula. Okay, now what I do, I replace this B by this relation. Let me write it down. It will be 1 by 2 m. B means what? A omega cos omega t plus what? Phi with whole square. So this will be whole square. But this square is for A, this square is for omega and for cos omega plus phi. So let me open the bracket. 1 by 2 m A square, and this is omega square, and I write on this is cos square omega t plus what? Phi. So this is your kinetic energy. So the kinetic energy is given by this relation. But let me replace the constant. Kinetic energy terms of another constant. So let me just use the symbol 1 by 2. Now you know there is a relation that you have learned, m omega square a square cos square omega t plus phi. You know omega m omega square we have replaced by a small k, this is small k, and this small k is also called what constant? Force constant. So in the last YouTube video you learned this particular topic of constant small k equals to m omega square. This means we can now even write the expression of kinetic energy. Now see, k equals to half a square k cos square what? Omega t plus what? Phi. So look at the expression of kinetic energy, but in terms of what? Epoch. So k equals to what? Half a square k, we can write this way also, small letter k, this is small letter k, cos square omega t plus what? Phi. So this is the what constant? This is a kinetic energy, and this k is what? A what constant? Spring of force constant, because the force which acts on the simple harmonic motion is a restoring force, and restoring force is also a what force? A conservative force. Remember this, what force? Conservative force. Okay. Now similarly we can calculate the what energy? Potential energy of the particles. And the potential energy of a particle in simple harmonic motion, yes, we can write by symbol U, or we can simply write PE, no doubt. And the potential energy, and we write this potential energy as elastic potential energy, half kx square. Half kx square is the elastic potential energy of a particle under simple harmonic motion. See, we have done this energy part in the chapter called work, energy and power. Okay, now let me just substitute the value. Half k. Now this x is the displacement of the particle, and as I said, displacement can be along x-axis, can be y-axis. Whether you write this as x or you can write y, both are correct. So, but the value of x, v or y, we have already done, and you know what is the value? The value is a sine omega t plus what? Phi, and I put it what? Whole square. Okay. Now let me open the bracket. Half k, small letter k, a square, and this is sine square omega t plus what? Phi. So children, I got the potential energy, and even I got the what energy? Kinetic energy. So I just add this energy with the sum of kinetic energy and potential energy means the what energy? The total energy. So I calculate now the total energy of a particle in what motion? Simple harmonic motion. And this total energy is expressed by E, and it's nothing but K plus U, calculate K plus U. Or I can also write kinetic energy plus potential energy, same thing. Okay, now kinetic energy, half small letter k, a square, and this is cos square omega t plus phi. See, this is the kinetic energy. So kinetic energy we have already calculated. Yes, this is the kinetic energy we already calculated, plus the potential energy is this much. It is half k a square what? Sine square omega t plus what? Phi. So I substituted both kinetic energy and potential energy. Now you can clearly see in the relation there is a constant. I mean there is a common. Half and ka square is common. Yes, half k a square is common. So inside the bracket I write cos square omega t plus phi plus sine square omega t plus what? Phi. And you know in trigonometry cos square theta or sine square theta of any angle is always equals to 1, which means E equals to half k a square. Now I replace this k even by this m omega square. So because K means what? M omega square, and there is already what? A square. Now see the expression of kinetic energy. I mean the total energy. The total energy of the particle in simple harmonic motion at any position, this is at any position, is given by E equals to half m omega square A square. So in the expression, m is constant, A is also constant, omega is also constant, means the total energy always remain constant or remain conserved, which means the total energy, which is also called the mechanical energy in simple harmonic motion, is always remain constant. So the energy conservation is even valid in case of simple harmonic motion. So the total energy always remain constant, and the total energy expression in simple harmonic motion at any position of the particle is given by the expression is E equals to 1 by 2 m omega square A square. Means whether the particle is at mean position or maximum position, at any position, the energy always remain constant. Means the total energy does not depend upon the displacement of the particle or the position of the particle. At any position, the total energy remain constant. However, the kinetic energy may change into potential energy, and potential energy get converted into kinetic energy, but the total energy always remain constant. So this is called total energy of the particle. Okay. Now in the next class, we do the same total energy with the help of graphical representation. Okay. And after that, we do important numericals. So the theory part of this chapter I have done, important theory part I have done it in details. Now in the next class, we do the graphical representation followed by the numerical problems. Okay. So with that, the chapter simple harmonic motion get completed. Thank you so much.